Again, we'll bring it up. There's the recording. All right, guys, welcome to Upgrading Smart Contracts. Let's do this. So the first thing is that, okay, immutability. We know that every transaction moving funds, contracts deployed, transactions, function calls made to a contract, their results are recorded in an immutable ledger called the blockchain. There's no way to hide or amend these transactions. And any node on the Ethereum network can verify the validity and state of every transaction. This is a good thing. This is the whole point of blockchains. But there's a downside here, which is that you can't upgrade things if they're immutable. So immutable code and contracts deployed to the blockchain, the source code cannot be changed. And we know from previous programming experience that it's a very good thing to be able to upgrade and change your smart contracts. Now, why is that? Well, let's take a look at some of the motivation here. And here's a historical example. And so there was this thing called the Parity Wallet. Has anyone heard of it? It was a multi-signature wallet. So basically a bunch of people, this hack happened in 2017, but the way a multi-sig wallet works is a bunch of people need to sign a message in order to transfer some funds out of a wallet. That's called a multi-signature wallet. And there was this version of a multi-sig wallet created by Parity, and it had a bug in it. And so it allowed an attacker to steal over 150,000 ETH. And the issue is that during the attack, there was a bug exploited in the Parity multi-sig wallet. These wallets were being drained of their funds, and the wallet was not upgradable is the issue. So it wasn't made in such a way that it could be upgradable. And so the only thing that the team could do was when they discovered that there was this actual bug, they went to try to exploit the bug and steal the funds before the hacker did, and then just redistribute the funds to their rightful owners afterwards. So this is sort of a motivation for why you would want something like an upgradability mechanism, where once you detect the bug, you fix it and you upgrade it. Instead of, in this case, they were able to exploit the bug and steal funds, but they might not be so quick in future incidents. All right, and then later another bug showed up with this is not exactly related to upgradability, but there's this infamous GitHub issue. Anyone can kill your contract on the Parity Ethereum GitHub, where basically this guy detected this bug, and he was like, he found some bug where somehow you can make it so that all the funds get trapped in these wallets. And then he literally just, this is some guy, some like developer dude. He was like, okay, I accidentally went and triggered it. And a lot of people had their funds frozen. And then he was like, I'm just a beginner developer. I don't really know what I'm doing. Please don't send me to jail. And I think he didn't go to jail, probably. So that's a little bit of history with Parity.
It's pretty funny.
Yeah, it's pretty funny.
So
yeah, go ahead.
So Parity is this like smart contract wallet.
Exactly.
Yeah. Okay.
Exactly. Yes. So now, if only there were a way to update the source code after the smart contract has been deployed. So, okay, it's not possible to upgrade the code of your already deployed smart contract, but it is possible to set up this proxy contract architecture that allows you to use new deployed contracts as if your main logic had been upgraded. Okay, so here you can see this is the user or the front end that's making the function call to a smart contract. And instead of directly going to the contract, this function call is routed through a proxy contract. And so all message calls go through a proxy contract, and then they're redirected to the latest deployed logic contract. And I should say logic contract here. And in order to upgrade, you deploy a new version of the logic contract, and then the proxy is updated to reference the new contract address. So it'll, instead of directing or forwarding message calls to logic contract 1, it'll direct them to logic contract 2. And that's considered an upgraded contract. And so the key concept to understand here is that the logic contract can be replaced while the proxy or this access point is never changed. So the proxy is never changed. Both contracts are still immutable in the sense that their code cannot be changed, but the logic contract can simply be swapped out with another one. So the wrapper can just point to a different logic implementation, and this is what we call a software upgrade with smart contracts. So that's the basic idea. Does anyone have any questions about that? Okay. That's the basic idea. And then here we have a problem, right? The first question is, how can the proxy expose the entire interface of the logic contract without requiring a one-to-one mapping of the entire logic contract's interface? So if my logic contract has function A, function B, something like balance of and transfer and whatever, right? Do we need to put all those functions into the proxy contract and say, hey, if someone calls a transfer on the proxy contract, forward it to the transfer function of the logic contract, and so on for every single function in the logic contract? This would be obviously difficult to maintain, prone to errors, and the interface itself would not be upgradable. Like we couldn't just add a function because again, we can't change the proxy contract. So if we require this one-to-one mapping, it seems like we would have some issues. So we need this dynamic forwarding mechanism. Have any questions about this? Okay.
I don't. Yeah, I don't know much about how the dynamic forwarding mechanism works, but yeah.
Oh, good. I'm glad you asked that. How does the dynamic forwarding mechanism work? So first, we need to understand two things about solidity here, because this is proxies and solidity. And we put these two things together to get how the dynamic forwarding mechanism works. The first is the idea of fallback functions. So solidity has this thing called fallback. You see, this is a keyword, and it's a function called fallback, and it's externally accessible. And in this case, it also happens to be payable. Like you can send money to the fallback function. And so when a function call to a contract is made that the contract does not support, right? So I call function blah on a contract, but there's no implementation for blah in this contract. The fallback function is called. And so you can write a custom fallback function to handle these scenarios. So you can run arbitrary code when a function is called that actually isn't supported in the contract. So the proxy contract uses notice this is called delegate proxy. This is one example of how a proxy can be done. It uses a custom fallback function, which redirects calls to other contract implementations. And so this permits this it's called a delegate proxy pattern, where the functionality is implemented in a logic contract outside the called contract, and the called contract or the proxy delegates that function call to the logic contract. So here's an example of the implementation. Really, all that's happening here, I don't know if I have it on another slide, but I think we'll get to this in a moment. We're going to revisit this bit of assembly. I don't write in assembly, although it's basically, if you're a real legit Solidity developer, you should kind of know assembly and know what's going on. But this is basically the whole implementation of the proxy in like 6-7 lines of assembly. 6 looks like. So we'll revisit this in a moment. So the other piece of this is delegate call. And you'll notice that it's on line 10, like this is the real work of the assembly. This is really where the the work is getting done. There's this delegate call opcode in the EVM, which allows you to forward a function call to another contract, but it's not the same thing as just calling that function in an ordinary way on that contract. You're actually forwarding the function call, but keeping the execution context to be the context of the called contract, right? So let's see if we can make that a little clearer. So delegate call is just like a regular function call from one contract to another, but the message context doesn't change. So delegate call keeps the same message.sender as in the calling contract. So for example, calls contract A, which delegates the call to contract B. Contract B won't think that, hey, it's contract A who called me. It'll actually think, hey, it's Cole who called me. And so in some sense, you keep the execution context the same as in the calling contract. And so in some sense, delegate call, this EVM opcode, runs the code of another contract inside the context of the execution of the current contract. I'm gonna wait for Amy to rejoin. Looks like Amy's got her own setup now. Nice. All right, can you hear and everything, Amy?
Not yet. I'll figure it out. Sorry.
No worries, no worries.
Here,
And so basically, here there's this mechanism where you can kind of load code from another contract dynamically at runtime. So when a call is delegated from A to B, the storage, the current address, the balance still refer to A, but the code is taken from B, and that's run to like sort of manipulate the storage, perhaps, or read from it, or change the balance of contract A. So let me say this in a different way so it sinks in, because this is really it's a slightly confusing thing at first. So what have we got? Yeah, so delegate call essentially runs the code of another contract in the context of execution of the current contract. So for example, it can be used to invoke code from a library, right? That's kind of what it means to use a library in Solidity, right? You use code from another contract, which is the library contract, and you run that code, but it actually modifies the storage and views the balance of the current contract. And that's it. So does anyone have any question about delegate call?
Yeah, it's cool. At first, I was wondering what the security implications were of being able to delegate a call using the same message.sender as the original call. Because at first that seems kind of problematic, that you can basically impersonate whoever's calling your contract on another contract. But then I realized when you explained that you're modifying the storage in the context of contract A as opposed to contract B, which you're delegating the call to. And so then it doesn't seem problematic anymore.
Exactly. Someone calls contract A delegates to contract B, but it's still contract A's storage which is getting modified. But you're right to pick up on the fact that it seems like it's easy to get this whole delegate call thing wrong. And in fact, that infamous parity bug, I think the second one, was just somebody using delegate call improperly. And so it's been used improperly many times in the history of smart contract hacks, and people who don't understand it, they tend to get hacked. And that's why OpenZeppelin, who is I think that's where this code example comes from. Their whole thing is, okay, we're going to really pay attention to the internals of these contracts and the security implications, and make a big library of different proxies and stuff like that, which are audited and secure, and then people can build on top of it. Yeah. So any questions about delegate call? We can make a note. We can actually search the parity hack. Let's see. So OpenZeppelin. And I think at the bottom, what they really say is you shouldn't have used delegate call here. Yeah, so here they go over. I can copy this and put in the Discord. Let me do that real quick. This is OpenZeppelin sort of post-mortem on the Parity Wallet hack. And they explain how it worked exactly. And they say solution is the attack could have prevented either by not extracting the constructor logic into the library contract, or by not using delegate call as a catch-all forwarding mechanism. So it's often I think an improper use of delegate call is actually what led to this parity hack here. And we can look at the details later if we want. But okay, that's delegate call. Now let's go back. Why are we going through all this? We're trying to see how the dynamic forwarding mechanism of these proxies works. So let's go forward. Okay, so review. Contract A delegates a call to contract B, executes the code of contract B in the context of contract A. So there's this message object, which is a globally available object. It's available in the execution context of any smart contract, and it stores something like message.value. That's the amount of ether that was sent along with this function call, and message.sender, the person making this function call, and that's preserved, right? And so also storage modifications impact the storage of contract A. Message.value and message.sender reflect those values of the person making the call to contract A, not of contract A itself, but all the logic is delegated to contract B. Okay, and so if we go back to this chunk of assembly that actually does the delegation, what happens? You can put this code into the fallback function of a proxy. It'll forward any call to any function with any set of parameters to the logic contract without it needing to know anything in particular about the logic contract's interface. So this is the dynamic forwarding mechanism. In essence, in this area here, the call data, meaning the function that you want to call and its arguments, right, is copied to memory. And then the call is forwarded to the logic contract with delegate call. It also sends along the gas. And then the return data from the call to the logic contract is retrieved, right? So, what's the value that was returned? And then the return data here is forwarded back to the caller. And that's how it works. Does that make sense? Do you have any questions about that?
I think superficially it looks good to me without looking too closely, but yeah, I think that looks good.
Yeah, superficially looks good to me too. I can't say I understand every bit of this assembly because I don't work with assembly on a regular basis, but we can kind of see that, okay, here's the result. We get the value back from the delegate call. This is whatever the logic contract returned. It's our result. And then if the result is 0, I think that means that it failed somehow. And so we'll revert, right? Otherwise, we'll just return.
Do you know what that underscore IMPL?
Oh yeah, underscore IMPL, that's actually part of the larger, contract, right? So that's not actually some keyword or anything. We store the address of the implementation or contract B, right? Okay. This here is contract A. And then we delegate the call to adder is set to implementation. So that's just
telling it where to go.
The address of the implementation. Telling it where to go, exactly. Do you have any more questions about that?
I think I'm good.
Okay. So then, yeah, so notice that maybe you didn't pick up on this exactly, or maybe you did, but the state lives in the proxy and the logic lives in the implementation, right? That's the whole idea. So an important thing to note is that the logic contract controls the proxy state, and the logic contract state really is meaningless. Thus, the proxy doesn't only forward transactions to and from the logic contract, the proxy also represents the pair's state. It represents the state of this proxy implementation pair. Okay, so the state is in the proxy and the logic is in the particular implementation that the proxy points to. So any high level questions about this whole setup? Okay, let's continue. So here's a first consideration, right? So a problem that quickly comes up when you use proxies has to do with the way in which variables are stored within the proxy contract. So suppose that the proxy stores the logic contract's address in its only variable is here, this public address underscore implementation. That's kind of what we just saw in the delegate proxy example. But now suppose that the logic contract is a basic token whose first variable is address public underscore owner. So both of these variables are 32 bytes in size. And as far as the EVM knows, they both occupy the first slot of the resulting execution flow of a proxied call. So when the logic contract writes to its underscore owner, because the logic contract's logic is being executed in the context of the state of the proxy contract, right? So if the logic contract says, hey, write this to owner, this address to owner, it's actually going to be overriding this underscore implementation because the logic contract writes in the scope of the proxy, modifies the stuff in the proxy. And so this can be referred to as a storage collision. Does the idea of the storage collision make sense? Cool. So what do we do? What we do is we randomize the slot in the proxy at which the implementation address is stored. So instead of storing implementation address at the proxy's first storage slot, which will basically definitely collide with whatever is stored at the first storage address in the implementation contract, what we do is we choose a pseudo-random slot instead. And it's sufficiently random that the probability of a logic contract declaring a variable at that same slot is negligible. And so we use this same principle to randomize the storage slot of whatever other information we need to store in the proxy, like who the admin is, because there might be some admin who can call the upgrade function on the proxy if you have an upgrade function on your proxy. And obviously you don't want that to collide with some sort of storage slot in the implementation, have it be accidentally overwritten. Now, there's this EIP. The question is like, okay, randomization seems pretty good, and there's such a large space of slots that you're probably not going to have a collision. But what they did is, they being the people who wrote EIP 1967, they said, we're going to actually choose a storage slot that the compiler can never sort of dynamically allocate. So you're guaranteed to actually never have a collision. And what do they do? You take the hash of this string, EIP 1967.proxy.implementation, cast it to a 256-bit integer, then take, treat it as a 32-byte value, subtract 1 from it, and you end up with this address that actually can never be collided with for some particular detail about how storage slots are assigned by the compiler. And so because of this, the logic contract doesn't need to care about overwriting any of the proxies, at least the implementation position, right? And that's it. So in this case, neither of these contracts needs to care about the structure of the storage of either. Do we have any questions about this?
Yeah, that's cool. I'm wondering just what it looks like in Solidity to. So here you're calculating the position, and you're storing that into implementation position, but then how do you actually tell Solidity to store a variable at that position, basically?
Well, let's look at it. So here's an implementation. Here's a reference implementation from EIP 1967. See if we can decipher it. So we get this implementation slot here, and it's equal to that value which we just discussed. And I guess you assert, well, I don't know what's being asserted. It's being asserted that the implementation slot is the correct slot, I guess. Implementation slot must be inherited from Proxy or ERC 1967 upgrade. I think it's right here. So here's how you do it in Solidity. There's this thing called storage slot. I don't know where that comes from. I don't think it's built in, but it's like a wrapper around some lower level functions, perhaps defined in Proxy or something like that. But storage slot dot get address slot implementation slot dot value equals new implementation. And that's what you do when you want to call set implementation with a new implementation.
All right, yeah, awesome.
So that's the way that they're doing that. This function upgrade to just calls set implementation with a new implementation and it emits an upgraded event. So we'll copy this and we'll put it in the Discord for further reference. Does that answer the question?
Yeah, definitely.
I wonder where storage slot even comes from. So search storage slot. That's the first instance of, oh, there's a library. There it is. Okay. Storage slot. What does it do? It's just some assembly. I don't even know what it does. Returns an address slot with a member value located at slot. And so it wraps it in address slot. And what is address slot? Here's a struct address slot. It just has a value in it. So it really is just some wrapper around some assembly code that just, I don't even know what it does. It accesses the slot. Yeah, that's my understanding of this so far. Okay, so if that answered the question, we can continue. What have we got? Okay, yeah, so that's what EIP 1967 does. Randomizes that implementation slot position to avoid clashes in the storage between the proxy and the logic contract. Okay, also on Etherscan, I don't know if you guys have actually noticed that Etherscan can know whether a contract is a proxy contract or not. Have you guys noticed that? So for example, let's look at this proxy contract. So it's called proxy wrapper because it's like a proxy, right? The code inside this contract is like proxy code. It's not the code of some implementation somewhere. So obviously the code is called proxy wrapper. It's literally just some proxy source code. It has some assembly it's literally that assembly, right? Switch results, revert, return, calls delegate call. It also has some other proxy related stuff, has an address library, it has storage slot, ERC 1967 upgrade. This is like a live proxy contract. But Etherscan is smart enough because of ERC 1967, it knows that if there is like an address that's stored at that particular storage slot, which is standardized inside this proxy contract or inside this contract, then it's probably a proxy, right? And that's the implementation that it's pointing to. So you can go to read as proxy. So if you try to read this contract, it's like, okay, there's no ABI, there's no really like public functions you can call. But if you click read as proxy, it'll say, hey, I noticed that at that storage slot, you're storing the implementation, which is this 0xD48, but we're not looking at that. We're looking at 0x729. So that's the proxy. This here's the implementation, and you can see, hey, here are all the functions of the implementation contract.
Sweet. Yeah, I think this probably wouldn't make sense, but I guess it seems like the way they have it set up here, you wouldn't be able to do like a proxy to a proxy, or else you would be having the conflicting storage slot again.
Well, why couldn't you have a proxy to a proxy? So let's say I have a proxy which points to a proxy, which points to implementation. What would the issue with that be?
Yeah, my thinking is just that for both proxies, they would use the same specific proxy storage address to store stuff. And then there would be some storage conflict, but I'm not sure whether or not that's true.
Well, it's sort of like this. So like, let's say you have, this is my understanding of it. Let's just take some notes. Take some notes right here, right? So we have a caller who makes it an invocation to proxy A, who makes an invocation to proxy B, makes an invocation to implementation. Okay, so I think the issue here really is that the caller says, hey, find me, redirect this call to the implementation at proxy A. Sorry, to the address of the implementation contract stored in proxy A. And that's proxy B, right? Which it seems like we're good so far. So it redirects that call to proxy B. But then proxy B, you can't access proxy B's storage is the issue. Because remember, when you do this delegate call from proxy A to proxy B, you're reading proxy A storage. So proxy B is going to be like, oh, delegate this call to the address of the implementation contract stored in proxy A, which is proxy B. So then proxy B is going to delegate to itself in this infinite circular loop. So this is the issue. This is the kind of an intricacy of delegate call. And we literally, in my work, we're like, all right, guys, let's do this. Proxy A, proxy B implementation. Because imagine that you have a bunch of proxy contracts, but then you have sort of like there's one proxy which points to all of them, which is somehow makes it such that if you upgrade one proxy, just call one upgrade, you can upgrade all of them at the same time. And we tried to do this, and then we realized, wait, like there's like a fundamental reason why that doesn't work. There are other ways to achieve that sort of like upgrade everything at the same time, upgrade multiple upgradable contracts at the same time, and have them all point to one kind of beacon contract, but that's another thing. Does that answer that question?
Yeah, definitely.
Okay. So do we have any questions so far about anything else? Okay. Cool. What else have we got here? Okay, so here's another, here's another issue. And this issue is a storage collision, not between proxy and implementation, but between multiple versions of the implementation. So for example, between implementation v0 and implementation v1. Notice that V0 has an owner, a balances, and a supply in that order. These are the storage slots. And then in implementation V1, let's say you upgrade the implementation, and implementation V1 has this new last contributor address, but it was added at the beginning, right? So it was added before owner, balances, and supply. So in some sense, when in the implementation of V1, when you go to sort of modify, I guess when you go to check who the owner is, when you go to modify last contributor, you're going to be getting who the old owner was, and you're going to be kind of overwriting that. That's the issue. So one other way to say this is like, okay, the unstructured approach avoids the storage collisions between the logic contract and the proxy. That's the IP 1967 that we just looked at. However, the storage collisions between different versions of the logic contract can occur. So in this case, imagine the first implementation of the logic contract stores this owner at the first slot, but the upgraded logic contract stores the last contributor at the first slot, the same first slot. So when the upgraded logic contract tries to write to this last contributor variable, it'll be using the same storage position for owner, and then it'll overwrite it. So that's an issue. How do we fix that? Any ideas?
It seems like you want to make sure last contributor goes at the end, basically preserve the ordering of the previous variables in storage.
That's right. You preserve the ordering. It's append only. You don't change it. And you kind of by hand have to ensure that, right? So you have to just be very careful. Have a lot of engineers look at it. Maybe write some tools to like check that things don't get reordered. But at the end of the day, you need to, as the engineer, make sure that things don't get reordered accidentally. It seemed kind of janky to me when I started, and this is kind of one of those janky parts of smart contract development right now. So we're going to look at.
Yeah.
Okay, so
here we don't have this problem.
Ah, interesting. You should tell us about that in a moment.
Yeah.
So correct storage preservation just looks like putting last contributor at the bottom. And so because the unstructured storage proxy mechanism doesn't safeguard against this situation. So it's up to the user to have these new versions of a logic contract extend the previous versions, or otherwise guarantee that this hierarchy is always appended to, but not modified. So for example, this is some of TrueFi's public code. This is an implementation contract, and it says, there's just a comment at the top. Warning, this contract is initializable. Stored variables are declared below. Removal or reordering of variables will result in storage corruption. So that's that. Any questions about this? Or do you want to tell us in Terra why this is not an issue?
Yeah, I could talk about it for a bit. So one thing is that first off, and I guess this is just Cosmos in general, it's not Terra specific. So in Cosmos, they support mutable contracts. So even like right off the bat, you don't really need a proxy contract. You can just upgrade contracts directly. And then as far as how storage works, for every variable that you store in storage, you basically give it like a key. So if you go back one slide, then like, for example, with owner, you would give it a key, and normally you just give the key, which is like basically the same name as the variable. So you could have the key being owner and the key being balances and the key being supply. And then when you do the version 2 of the contract, as long as you keep the keys the same, the storage accesses will be in the same position. So you don't have to, it's basically like the way that slots are determined is different, and it's not done in the way that it's done in the EVM. It's done based on like a key slotting style.
That seems like a pretty good design. I wonder why the EVM just kind of lays it out linearly.
Yeah, I don't.
Maybe it saves space or
Yeah.
something.
I think EVM is much more efficient, like space compact. I don't know for sure, but like one example is like in Cosmos, the limit for contract size is like 600 kilobytes, and I think on Ethereum it's like 30 kilobytes or something like that. So like I think in general EVM tries to make a lot more optimizations. So this might play into that somehow, but yeah, I'm not positive.
Gotcha. Okay, that's interesting. I appreciate that perspective. It's good to know how it works in Cosmos. I'd be interested if you would do a presentation on writing smart contracts in Cosmos.
Yeah, yeah, I could
That'd be
definitely
really cool.
do that. I spent a lot of time running into some edge cases sometimes. Yeah.
Nice. Sweet. Okay, what else have we got here? So, okay, so here are some other things, some other caveats about creating a proxy, right? So the first is that in Solidity, code inside a constructor or part of a global variable declaration is not part of a deployed contract's runtime bytecode. So the constructor's code is not part of the bytecode when it's deployed. So as a consequence of this, this code is executed only once when the contract instance is deployed, and the code within a logic contracts constructor will never be executed in the context of the proxy state, which is what you need. You need to be initializing the proxy state, right? Not the logic contract state at deployment time. So to rephrase, these proxies are totally oblivious to the existence of constructors defined in the logic contract. It's simply as if they weren't there for the proxy. So how do we solve this? It's pretty easy to solve it, right? You just move all the code within the constructor to a regular initializer function whose bytecode is part of the overall deployed contract's runtime bytecode. And so you have this function called whenever the proxy links to this logic contract. For example, when it's deployed for the first time, this proxy implementation pair, or when upgrades happen, if you need to reinitialize stuff. Special care needs to be taken with this initializer function so that it can only be called once. This is one of the properties of constructors in general. So that needs to apply to initializers here. And that's it. So you can create a simple initializer modifier in Solidity. And a modifier, in this case, the modifier just has some code to ensure that this function is only called once, and subsequent invocations will cause a revert to happen. Okay, and that's just kind of what this initializer modifier here is. And later on in this contract, right, I think in this initializable superclass, this initializer modifier is declared. That's all that does. So that's the idea behind replacing constructors with initializer functions, because constructors really have no access to the proxy state, but the initializer needs to access and initialize the proxy state. That's just a caveat here. Have we got anything? Oh, do you have any questions on that?
Yeah, one thing that's coming to mind, I don't know if you'll talk about this later, but I've heard that a lot of the bugs that come up with proxy contracts have to do with this constructor caveat. But I don't really understand what the problem was. Do you know much about that?
Yeah, I mean, there's an issue, which is what if you deploy a proxy and its implementation, but you forget to initialize the implementation.
Yeah.
Right. The implementation's initialize function has to be publicly callable. And so it might be the case that there's like a two-step process to deploying a proxy to contract, which is you deploy it and then you initialize it. Some people forget to initialize it. And so let's say one of the things you need to initialize is owner of this contract or person with all the permissions. Yeah. Somebody could see an uninitialized proxy contract, initialize it themselves with the wrong values or malicious values, and that's a hack. I think that has happened.
Okay, gotcha. Yeah, I think that's what I was thinking. Sweet. Yeah, that makes sense.
So what else have we got? Okay, here's one last issue. I think, this seems like it was a very dense presentation. I think it was. So we're getting to the last issue here. There are clashes between functions. So for example, imagine there are clashes between functions defined in the proxy and functions defined in the implementation. Previously, we looked at clashes between storage slots, and we used this sort of pseudo randomization scheme in order to mitigate or eliminate that problem. But there are function names, right? How do you solve that issue? Function names are not stored at some storage slot, right? When you call a function name, what happens is you basically take like a hash of the literal string name of the function plus the types of the arguments and the number of arguments. And that becomes like a 4-byte function selector. And that actually is the thing that's like determines the uniqueness of the function. That's like the unique name of the function to the EVM. And you could have two functions with exactly the same name and arguments in both the proxy and the implementation. Imagine that the proxy has a function called upgrade2, which takes an address, and the implementation has a function called upgrade2, which takes an address. So upon a call to that function, did the caller intend to call the proxy to actually upgrade the implementation? Or let's say this is some like play to earn game on Ethereum, and they wanted to like upgrade to the address of some shiny new NFT weapon or something like that, right? It's not clear if the person calling this was the proxy, like the person trying to upgrade the proxy, or someone actually interacting with a logic contract. Does that make sense? Does anyone have like a proposed solution or something they can think of that would mitigate this?
Yeah, I don't really know. It seems like you just have to name the functions differently, but aside from that, I'm not sure.
Yeah, avoiding manually avoid these collisions by not naming the functions the same thing. That's one option. Let's see how this is dealt with. This is some detail about how clashing can happen among functions with different names. We'll come back to that in a moment if we want. But really, the solution is this so-called transparent proxy pattern. So it get another layer of kind of complexity here, but it's that a transparent proxy decides which calls are delegated to the underlying logic contract based on the address of the caller, i.e. message.sender, right? So you store, like the proxy will store the address of the admin of this contract. And if the admin calls upgrade2, it'll actually call the upgrade2 function on the proxy. But if a user, someone who's not the admin, calls upgrade2, it'll forward that call to the implementation. And if the implementation is that play to earn a gaming contract, you'll get your shiny new NFT weapon or whatever. That's it. So if the caller is the admin of the proxy, the address with the rights to upgrade the proxy won't delegate any calls. It'll only answer messages that it understands, like upgrade2 in this case. But if the call is any other address, it'll always delegate the call, even if it matches one of the proxy's functions. So let's look at the following table, assuming a proxy with an owner function and an upgrade2 function, and then it delegates calls to an ERC20 contract with an owner function and a transfer function. So here you can see, here's the proxy. Basically, if the owner calls the owner function, it'll return proxy.owner. But if someone else calls the owner function, it'll return ERC20.owner. Oops. Now, if the owner calls upgrade2, it'll return proxy.upgrade2. If someone else calls upgrade2, it'll fail because ERC20 has no upgrade2 function. If the owner calls transfer, it'll fail because when the owner makes a call, the proxy is looking to actually invoke some function, on itself defined within the proxy contract, some like proxy related function that doesn't exist, so it fails. Someone else calls transfer, it's going to delegate that to the ERC20 implementation contract, and that'll call ERC20.transfer. So that's the sort of idea. Owner has some special identity. When the owner makes calls, they're invoked directly on the proxy. There are also other like ways of doing this, right? This is not the only way to do it. So I think recently, like, I don't know, a year ago, OpenZeppelin, I think there was some EIP about UUPS proxies, and this does things in a slightly different way. I think that we can look into that in a future video, but I guess, or in a future like lecture or whatever. But imagine like there is kind of an overhead, right? Like 99% of the calls will be from people who are not the owner, right? And they'll all be delegated. However, they'll be delegated to the implementation, right? However, because you have this thing where you need to check on every call, am I the owner? Is the caller the owner or someone else? That's like an overhead that slows down basically every call. It makes every single call more expensive. Every single non-owner call more expensive. So maybe you could flip things around and make calls from the owner slightly more expensive and somehow not do that check. And that's what this universal upgradable proxy standard does. I didn't prepare anything about that. I think we don't quite have time to get into that, but I'm happy to do a future talk on that because it's interesting. So do you have any questions on this?
Yeah, it looks good. I guess I'm wondering what it looks like at the code level, but aside from that, yeah, it makes sense.
Okay, let's root around at the code level and see what we've got. So Open Zeppelin, Proxy, GitHub. Oh, transparent upgradable proxy. What's that? Okay, so here's Proxy. So it provides a fallback function that delegates all calls to another contract using EVM. So this is the one we just looked at, right? There's this underscore delegate kind of helper function, which does that magic bit of assembly that does the whole delegation. There's an implementation view function. There's the fallback function. Here's the actual fallback function, which calls this fallback function, helper function, blah, blah, blah. That's the thing we just saw. The question is, how does the proxy, the transparent upgradable proxy work? Okay, so this contract implements a proxy that's upgradable by an admin. Okay, so if any other account other than the admin calls the proxy, the call before is the implementation, even if the call matches one of the admin functions, this is what we just talked about. Might as well read the comment though. If the admin calls the proxy, it can access the admin functions, but its calls will never be forwarded to the implementation. All right, so the admin account can only be used for admin actions like upgrading the proxy or changing the admin. So it's best if that's a dedicated account. It's not used for anything else. All right, so they recommend having the dedicated account not be like an externally owned account, right? Like a MetaMask address or whatever, but have it be an instance of the proxy admin contract. And if you set it up this way, think of proxy admin instance as the real administrative interface of your proxy. So oftentimes you actually deploy a proxy admin contract to be the admin, and then you call the admin or whatever. And then the admin calls the admin functions on the proxy. But what is going on here? The constructor of this proxy has an admin address, has a logic contract address, has some data. I don't know what it does with the data. It instantiates this ERC 1967 proxy with some data. There's a modifier if admin. There's a getter function for the admin, getter function for the current implementation, function to change the admin, and you have to be the admin in order to change the admin. Or the admin can call this function. Where is the part where it says, where it checks who the admin is?
I think it was up in the if admin modifier.
I see. So it'll delegate the call, but if the sender is the admin, it'll just continue and run that code. I see. So any of these admin functions like change admin, upgrade to, involve the if admin modifier. The if admin modifier will delegate it if you're not the admin.
Sweet. Yeah, that was helpful. Thanks.
There you go. And so, yeah, and so there are also these UUPS proxies, which are they ensure upgrades are not turned off accidentally. There are some like performance improvements, but there are trade-offs there too. We can talk about that later. Have we got anything else? Oops. That's it. Here are some sources. And that's the end of that.
Awesome.
You stop the recording.